I'm too tired to ask you all over and over again to be quiet. Thank you. You can see how tired I am because I didn't have time to put the colors of my clothing onto the preliminary slides of my presentation. It's a very sad and exhausted professor you see in front of you. Okay, so we're going to start out by finishing up this idea about overconfidence and this possibility that we might actually be able to explain something that is apparently quite irrational with a model that is perfectly rational. And then we'll start talking about social preferences, which is the main topic for the next 3 lectures. And in a move that may seem somewhat counterintuitive, we're going to start by reviewing game theory. And the reason why is because social preferences, which is how you feel about outcomes for others and potentially even how your beliefs about what other people's preferences are for you and your beliefs about whether or not they're nice or nasty, all of that is stuff that A, comes into effect in large part in game theory, and B, in order to test it, in order to test your preferences for other people's outcomes, we have to put you into a game theory situation, right, where you're interacting with another person. So we'll crank up game theory, and then we'll start talking about social preferences. And the very first thing in the title of this lecture will be the very last thing we get to, which is the Charness Rabin model of distributional preferences. I had assigned this paper as a required reading for this section of the class. It's not a hard paper to read. The model is very simple, and I would encourage you to read it because it's chock full of really interesting evidence. They run about a bajillion different experiments to test this model of social preferences, and you're going to need to get familiar with the model. Okay, so let's backtrack, and we're still talking about probability inference. And I showed you a bunch of evidence last time that suggests that people are overconfident about their own ability on easy tasks and underconfident on hard tasks. Okay, and so I started to introduce this model from Moore and Healy to explain why that might actually be, in some sense, quote unquote, perfectly rational. And it's obviously, it doesn't really satisfy what we think of as the broad definition of rational expectations, because it means that you have a belief that is incorrect, but it could be generated from a rational application of Bayes' rule. So let's see if we can understand how. All right, so you're taking a test, and it's got some difficulty level D, and what D actually is that on this test that you're about to take, there will be some class average for that test, right, D. So that if D is big, the thing's going to be scored between 0 and 100. If D is close to 100, it means that was an easy exam, right, which we captured by the fact that everybody got a high score. This would be midterm 2 in this class. Well, that easy, but it was easier midterm 1. And it's going to have some mean, MD. So this here means that it's distributed normally, right, over all possible exams that you've ever seen or could see. There's some normal distribution with a mean of MD and a variance of VD. Okay? So let's just stick something up here that looks like that. So this is the distribution of class averages on different exams, an infinite number of different exams that you have seen or could see. And it ranges from 0 to 100. And then this is telling us that there's some distribution of probabilities as to how likely it is that the class average will be all the way up at 100, all the way down to 0, or somewhere in the middle. Okay? And because this is normal, which is a symmetric distribution, the mean is going to be smack in the middle there where it peaks out. Okay? So that's MD. That's the average, class average score across all exams. Then we're going to let you have some distribution of idiosyncratic deviation from the mean. And it's going to be normally distributed with a mean of 0. This is just arbitrary. It doesn't change the qualitative results of the model, it just makes it easier. So basically what this is saying is that on any randomly chosen exam, whoops, sorry, that's not how I want to draw that. I want to put that in the middle. On any randomly chosen exam, your score is going to be some combination of the class average and then whether you were a little bit above or a little bit below the class average. And that's going to be sort of, not exactly random, but it's going to be just probably, it's going to be stochastically distributed around a mean of 0. Okay, so your idiosyncratic deviation from the class average on any given exam is going to be something like that. They're both normally distributed, right? So let's say that this one has a variance of VB and this one has a variance of VL. And what we're going to do is we're now going to give you a specific actual exam, okay, which we can think of as being randomly selected from this distribution. It might be above, it might be harder than usual or easier than usual. We don't know yet. And then we're going to let you take the exam and see your score, but not see the class average. Okay, so your score xi is going to be, the actual score. Let's say that we know the person taking the exam doesn't know, but we know that the actual exam. Sorry, I'm going to put that a little further down. That the actual exam this person is going to take has a difficulty level there, D. Okay. And then this person is going to do maybe a little bit better, a little bit worse. We're going to say, just for the sake of argument for now, let's let the person do a little bit better than the class average on this exam. So just as a preliminary example, let's say that their LI is there. So what does that mean about their score over here between 0 and 100? It was the class average for the exam they actually took, which they don't know yet, but we do, plus this piece here, right? And so we can think about superimposing that distribution sort of on top of this point here, right? And this person got, right, so this is sort of the distribution of LI, and I've superimposed it, right, because LI is the deviation around the class average for the exam. So this person's score is D, the class average for the exam, plus their little idiosyncratic piece, which is Li, which together gives us their actual score xi. Okay? I know it gets a little cramped in here, but can everybody sort of see that relatively clearly? What we want to use Bayes' rule for is this. Okay? The person is trying to get a read on whether or not that was a hard exam and whether or not they did well. Okay? So the way we're going to think about that is, this person, what did I just do with that chalk? This person knows their own score, right? They know xi. They don't know how far above or below the mean they are for the class for that exam, but they know the average. So they know this, their own score, and they know how hard exams are on average. Okay? This beastie here is what's called the person's prior. That's their prior belief about the most likely difficulty level of the exam before they take it. This thing here is the signal that they receive, which is their own score. And the thing we want to infer is what will be their posterior belief about how hard the exam was on average for everyone else in the class. Okay? So that is to say, what should you infer about the class average D given your score xi? Right? So you know this thing, you know that thing, you don't know this thing, and you want to guess what it is based on the two pieces of information you have. Right? So this is exactly the same kind of setup as you've gotten an HIV positive test result. You don't know whether or not you're actually HIV positive, but you know the base rate probability that you're HIV positive over the whole population. So you have two pieces of information, the base rate and the signal. Here, the two pieces of information you have are your prior belief about the average of the distribution and your signal. But it's exactly the same setup, and we can use Bayes' rule to give us the answer. Okay, so here's just a piece of information that I'm going to just give to you without an enormous amount. I can show you the proof if you desperately want, but I don't think it's going to be a useful way to spend our time. If the expectation of D, if the average D across all exams, right, is MD, that mean, we call that the prior, and XI the signal. And then if we define these two things, HD and HL, as 1 over the variances, right? So VD is the variance, HD is 1 over the variance of D. So you can think of those things are called the precisions of the prior and the signal, right? So HD is the precision of the prior, and HL is the precision of the signal. Which is, right, so think about this. If the range of difficulties on the exam is really, really wide, it's highly likely that you'll get an extremely hard or an extremely easy exam, then the variance, VD, of exam scores is really big, and the precision of the prior, HD, would be really small. It's not a very precise piece of information, right? Whereas the distribution of the signal, right, is VL, okay? Sorry, not the distribution of the signal, but the distribution of your idiosyncratic part of the signal. Let's suppose that that's really tight. You're always really close to the mean. Sometimes a little high, sometimes a little low, but very seldom do you really nail an exam or really bomb it relative to the rest of the class. In that case, VL would be quite small, right? The variance of this thing is small, and that would mean that HL, the precision of the signal, would be really high, okay? And so what Bayes' rule does, if you apply Bayes' rule, so here's D, it's distributed this way, here's Li, and your score is distributed, is basically the class average plus your little idiosyncratic part, and those are both random, then your posterior belief, right, your conditional expectation of D, your best guess as to what D actually is, the actual difficulty level of the exam, given what you've already seen, the signal that you've seen, which is your score, right, is equal to this. Okay, and there's some big scary proof of that, and it's a very neat result because of the normal distribution. I don't know how many, if you've taken a bunch of probability theory, you may start to realize that the normal distribution looks like really strong evidence that there actually is a God, because it does so many clever things, right? It's like, how could there be this one distribution that just does all of these amazing things? And not the least astonishing of which is that it perfectly describes the Brownian motion of molecules in space, I think, I don't know, in a gas or in any phase. So it's this really astonishing thing that seems to explain a lot about reality. And then also, for economists, it has the benefit of just getting lots and lots and lots of bizarrely simple results. So one of the bizarrely simple results is that when you make the simplifying assumption that the signal and the prior are normally distributed, okay, then what you get is that the posterior belief, according to Bayes' rule, is just this mixture, right? There's the prior, there's your signal. And what are these weights here, okay? That's the weight on the prior. That's the weight on the signal. Okay, so what is the weight? HD over HD plus HL. So that's the precision. This is where I wish the screen was down here. It's the precision of the prior as a proportion of the sum of the precisions. Okay, so it's a number between 0 and 1. And if this prior HD is more precise, right, if exams don't vary that much, then that's a fairly big number, right, because that means that the precision of the signal is big relative to the sum of the precisions. And likewise, if the signal is very imprecise, because your performance is like, oh gosh, I don't know, I got a high score, but that could still be below the average, because sometimes I just bomb exams, then again, the weight on the prior, it will be higher, right, because it's divided by a larger number. So basically what this does is it says, put more weight, right, so that the posterior belief about how hard the exam was is going to be in between MD and XI, right? I mean, you've got one piece of information which is here, you've got another piece of information which is up there. Your best guess after getting your score about how hard the exam was going to be somewhere in between those two. And where exactly it is, according to Bayes' rule, depends upon which piece of information is more precise. So if you know that your signal is usually very precise, that you're usually pretty darn close to the class average, then your best guess of the class average is going to be over here closer to X1, because the weight on the signal is going to be bigger than the weight on the prior, right? And the opposite of that is that if your performance is not a very good predictor of the class average, but the class average is usually pretty close, the exams don't vary that much, then you're going to put more weight on the prior and say, well, I know I did really well on this, but sometimes I'm just totally out of touch with the rest of the class, and so that doesn't necessarily mean that everybody else did really well. So that's the sort of perfectly rational application of Bayes' rule to inference about some underlying process that you can't observe given one signal, and you can extend it to a set of signals, right? What if you knew several people's scores, and you knew how well they usually do? Then you could do a series of these updating processes, and it would all look mathematically pretty much the same. So you can kind of already see what Moore and Healy are getting at. You don't know how hard the exam was. All you know is that you did better than the average of class averages on all exams. So by Bayes' rule, your best guess of how hard the exam was is that it must have been the class average must be a little bit lower than mine. My best, not that it must be, but that my best guess, right? My best guess is based on my scores that the rest of the class must have done better than, this must have been a bit easier than the average exam, but still, I think the class average is probably less than mine. That's my best guess, okay? So by Bayes' rule, if we think that people's estimation of the most likely class average is their, the conditional expectation of class average given their signal, then they're always going to think that they did better than the rest of the class as long as they did better than the average across all exams, right? Which is to say, on easy exams, which is those are the times they're most likely to do better, right? So MD is the class average for the average exam. So if you drew an easy exam, it's likely that your score is going to be above MD. It might or might not be above the class average for that exam, but it's likely to be above MD. And so more often than not, when you pick an easy exam, Bayes' rule is going to cause you to infer that you did better than average, right? Which is what this slide says, okay? So this is the example I just went through. If the test is easier than the average test, and you do, well, actually, this is a slightly weaker example. And I said you do so-so, which would mean that Li was 0, right? So D is greater than MD, like I've got over there, and then Li is equal to 0. So I've got you, instead of being above the class average for this exam, just being spot on, right? In that case, Xi, your score is going to be greater than MD. So you infer your posterior belief about the class average for this exam is that it's going to be between the average of across all exams and your score, which is greater than the average across all exams. And more importantly, puts you above your best guess of the class average for this exam. And then if you pull a test that's harder than the average exam and you do so-so, right, which was represented numerically there or mathematically, then in that case, your score xi is going to be less than the average class average score across all exams. You're going to do your score is going to be down here somewhere, and your best guess of the class average for that exam, again, is going to be in between your signal and your prior belief, but in particular, you're going to place yourself below your best guess of the class average, so you're going to think that you underperformed on hard things. Okay? Does that make so much sense that there's just not a question to be asked, or does it make so little sense that nobody knows what question they would ask? The latter. David says it's the latter. Yeah. Unless the precision of either the prior or the signal is exactly 1, unless one of those things is perfectly precise and the other is perfectly imprecise, then it's going to be somewhere in between the two. It's never going to be at either end of that range. Yeah. Now, you might think that this is a special case and that this is only true when the distributions are normal. And that's not correct. It's just that the math comes out super, super simple when we assume that the distributions are normal. The result would be qualitatively the same for any, well, I don't know for any distribution, maybe some pathological distribution that breaks this, but for a very wide range of distributions, I believe it's correct to say that the result is going to be basically the same. That if you draw an easy exam and do well on it, or at least don't totally trash it, you're going to conclude by Bayes' rule that you did better than average. And that if you draw a hard exam, you're going to conclude that you did worse than average. Right? And it's not that you're going to be certain you did better than average or certain you did worse than average, but that your best guess is going to be that you did better than average. So then these guys actually did an experimental test. This paper is on V-space under non-required readings, and they actually did their model actually explains a whole lot more than this. Okay? It turns out that it's not only is it true that once people have seen their score on an exam that they think that they did better than the rest of the class average, it's also true that before they see their score, they think they did worse than they actually did. So they underestimate their own performance before they see their scores, and then once they see their scores, they overestimate how good they are relative to the rest of the class. Okay? And the model in the paper is more detailed than this, but it uses exactly the same logic to explain why perfectly rational Bayesian updating would cause you to do both of those things. So here's what they did. They gave a bunch of, I hope they paid these people a lot, because this must have been really tedious, 18 rounds of 10 question trivia quizzes. These are different quizzes, so that should have said quizzes. So out of 18, they had 6 chunks of 3 quizzes, right? And in each chunk of 3 quizzes, there was an easy, a medium, and a hard. Okay? And they were then randomly distributed, so that people got different quizzes in different blocks. But in each block of 3, they got an easy, a medium, and a hard. And after every single quiz, when you'd seen your score but had not seen the average score for the rest of the group, you would be asked, so they actually they asked them a bunch of things, but one of the things they asked them was, for one randomly selected other subject in this group, they're all sitting in a room at computer terminals, like a typical experimental lab if you've been in one. So they're not talking to each other, they don't know each other, but they're all in a room together and they can see each other. And they know that they basically just, undergrads who've been pulled off the street and given $15 to take a bunch of quizzes. And then they're asked to give the probability for this randomly selected other person, to sort of like state a probability distribution, that their score on this quiz was a 1, a 2, a 3, 4, etc., right, up to 10. And the way this is done is that on this little computer, they're asked to sort of like fill in a histogram of like, well, if you think that was a medium exam and the other person that's been randomly drawn is most likely to be average, so you'd say, well, most likely I think they probably got a 5, but I think it's somewhat likely that they got a 6, a little bit less likely that they got a 7, and on like that. And so subjects were asked to sort of, on a computer, to shift around these little sliders until they got a histogram that represented their best guess as to how this randomly selected other person did. Right? And so since they didn't know who this other randomly selected other person was, then that's basically the same as asking what they think the average score for the class is. And basically, if the average of this distribution, which in this case would be 5, is below the score you got, that means you overplaced yourself. And if the average is above the score you got, that means you underplaced yourself in the distribution. And sure enough, what they find is exactly what the model predicts, which is that on easy exams, people on average overplace themselves by 0.5 point, and on hard exams, they underplace themselves by almost 1.5 points. Yeah? And they're pretty much spot on for median exams, which is to say, if your score was MD, you would not seem to be overplacing or underplacing yourself. So then this is the big question here, right? In terms of sort of the big concepts of this class. If we call Bayes' rule, or Bayesian updating of your beliefs, the rational model, because that is mathematically the correct way to infer the most likely difficulty level of the exam, and an appropriate, a mathematically correct application of that rule causes you to basically be more or less always wrong, right? In this very predictable, understandable, reasonable, the term they use in the paper is reasonable. Reasonable people would do this. So they're sort of sidestepping the question of rationality. And I think that the reason that they sidestep it by using the word reasonable instead of rational is because it's very hard now to think, just conceptually, about what we mean by rational here. When we talk about rational expectations, what we mean is that people have a correct belief about how likely things are. Right? That people's expectations about, say, for example, the class average are correct. When we say rational expectations, we don't mean that they applied Bayes' rule. We mean that they got the answer right. And this is a situation where using Bayes' rule correctly systematically gets you the wrong expectation. Okay? So we're really a little bit adrift here. And I have no idea what sort of the consensus among behavioral economists, or even if there is a consensus among behavioral economists, as to whether or not we should call this over and under placement